let's start by just getting it. So we know the magnetic field is a function with respect to time of B naught plus B1t. For your convenience, we restate Faraday's law here. Oh, thank you very much. I appreciate that. Where's the question mark? Well, a whole lot of stuff there. Oh, part A. Find E as a function of r and t, the electromotive force around a loop that is a distance r from the z-axis where r is restricted to the region outside the iron rod as shown. Take the direction shown in the figure as positive. Okay. We don't know what the area of the iron rod is or what its radius is. It just says we have a cross-sectional area A. So if this is the piece of iron and we are restricting our Faraday's law to being outside the iron, I'm just going to draw my area something like that so it wraps around the outside of the iron. That's what's shown in my picture. Is that okay with you guys? And I have this value r here that represents the radius to this loop that I've drawn, and I'm going to use a loop for my Faraday's law to calculate flux, but there's a cross-sectional area A for the cylinder. So starting with my calculation of flux is going to be the integral of B dot dA. Now, I get that B is a function of time, but for calculating flux, I don't need anything there but B. It doesn't change over the area, it changes over time. So I could even write this as the flux of B as a function of T dot dA, but all I am concerned with is figuring out, is the magnetic field the same everywhere within my area? And then I need to make careful consideration of my area. I can say this, no, the magnetic field is not the same everywhere within the area of the loop. That's true. But they tell me in this problem that the magnetic field is confined to just the piece of iron and is not outside the loop, which means that the magnetic field is just in this shaded region, which means that there's flux there, but there's not necessarily flux out in here. So the only area that actually contributes to the flux is the area of the cylinder. You guys follow that? Any question about that? I could draw this different if you want to see that better. You know, I would draw it like this, looking down the bit of the cylinder with my loop being out here. The only area that contributes is this area. So when I calculate the flux, my flux is going to be B as a function of T times A, which is the cross-sectional area variable I'm allowed to use, times the cosine of 0 degrees. I'm just going to assume that the flux for the loop is upwards because the magnetic field is upwards. That's the flux. It's not the EMF. That's the flux. To calculate the EMF, I need the time rate of change of the flux. Now, yeah, I know, negative sign and all that garbage, but let's just hold off on that for just a minute. I guess we'll put negative out here. It's one loop, so I'm going to assume that we all know n is 1. So all that's left for me to do is recognize I need the drop in my function and take the derivative with respect to t. So I'll get minus a times b1. That's it. Is there a part B? All right, due to the cylindrical symmetry of the problem, the induced electric field can depend only on the distance r from the z-axis where r is restricted to the region outside the rod. Find the field. All right, that's going to be a little bit more interesting, so I'm happy to do that. I am a little bit out of space here, so am I okay to pop to another page real quick? So, popping over to another page, I want to just briefly kind of sketch this again. And we talked a little bit about this on Friday. Not on Friday. I'm not even sure when we talked about it. My days are all confused now. But it had to be last week. But there is an electric field. That's what's causing this Faraday's law. But we only tend to see the electric field if we have a magnetic field that is changing with respect to time. And that's what we have. Our magnetic field is changing with respect to time, which means that our EMF is also equal to E dot ds, where in this case, ds represents an integral taken around the loop that I've drawn here, R. Now, again, drawing it in such a way that it's kind of pointing at you. We've got a magnetic field looking like this. That's out of the page towards us. And my loop is concentric. I mean, that's concentric. I know it doesn't look concentric, but we're going to assume it is. Is that okay? Good. And the radius, R, like so. The electric field has to be that way, that way, that way, that way. I just used the right-hand rule on it. Put my thumb in the direction of the magnetic field, and my fingers kind of curve like that, so that's got to be the direction of the magnetic field. Is that right? Are you sure I'm doing it right? I may be trying to trick you. Would you like to take a moment and see if my electric field is in the correct direction? So I am trying to trick you. The head's bobbed. Yeah, that's right. Sure, because it felt right. Put your thumb in the direction of the magnetic field, fingers curl, but that's not what happens. Everything I drew here is wrong. The electric field, just like any current that'd be generated in a wire loop that is there, would have to generate a magnetic field that would oppose the change. So if this blue line were a metal wire that was wrapped around this cylinder, the current in that loop would have to oppose the change in the magnetic field. And the change in the magnetic field is to increase it out of the board. So that requires a magnetic field produced by the loop that is in direct opposition to that into the board, which would require a current in that direction. Now, even though there's no current and no metal loop, that means that the electric field would have to be in this direction. That's not what the question's asking me. The question just wants what the magnitude of this electric field is. But when it comes to figuring out its direction, which I guarantee is something you will have to do on your next test, you need to be aware of what is being asked of you. So if you didn't write those things down, either because you already knew it or because you don't need that information, fine. But if that was news to you and you bobbed your head a minute ago, which was a whole lot of you, that means you were keeping right up to that point. And then you just said, yeah, Mr. Sheldon, I'm sure he's right. Do I need to go through that again? All you honor grads are sure? I know your numbers now. I can expect more of some of you and less of others. So, and that's in the video. So, moving right along, I'm pretty sure we have minus B1A as my flux from the prior portion of the problem. I think that because of the uniformity of the question, we can move the electric field out of the loop. Although there's a dot product there, I think I can state unequivocally that the electric field will be tangent to that loop at all points in the loop, which means it will be in the direction of the loop, allowing me to throw in a cosine 0 degrees here. Don't throw away dot products, please. Be aware of them, where they exist. Just be careful about them. That's one of those things that the problem slips in because you get complacent about it. Put that even in your notes. This is a dot product. The electric field and the direction of your loop have to be considered when you're calculating the electric field from a changing magnetic field. This is one of those hidden gems. It's small. It's such a small curricular point. But man, when it shows up on the test, people lose their minds. It's like, what? Let's not lose our minds on this one. This one's relatively straightforward. It's probably always going to look the same because all we're going to be left with is for us to add up the length of the loop, which in the case of this problem is 2 pi r. So that allows me to solve for the electric field minus B1A over 2 pi r. That's the end of the problem. Some kind of commonality here. Like I said, this was on, something like this was on the exam years ago. Did I do a good enough draw on that? And then the magnetic field does something like that, where they want you to say the magnetic field is at a 45-degree angle to the bend. Oof, that's just rough. Mean, right? Terribly mean. I'm going to draw this a slightly different way, if you don't mind. I think if I draw it a different way, it will assist you in understanding how to go about this problem. I'll remind you, flux is a scalar. So we are trying to figure out how much magnetic field passes through our area. Now I get that our area is kind of wrapped in 3 dimensions all of a sudden. But if I were to draw this from the side, that's not right. Let me be more pragmatic. How long would this be? I'm drawing it from the side on purpose. Can you figure out how long that would be? This is looking at my thing bent like that. It's 90 degrees, and I'm trying to find out this length. It's probably got something to do with the square root of 2, right? I'm thinking it's, I don't know, 2 times square root 2 times 5? Is that it? Because this part, no, that part would be 5 divided by the square root of 2. And then I need 2 of them to go all the way across. So that's how big it would be. So the end result would be root 2 times 5. You guys follow on that? If not, I could be more explicit. I just draw this out. Correct? When I draw that out, this side has to be shorter than 5. That means 5 divided by square root of 2. I don't have to do any trig for it. Just is it shorter or bigger? If it's a bigger part, then it's 5 times square root of 2. If it's a shorter part, it's 5 divided by the square root of 2. It's a lot faster that way, for me, my mental math. So unless you have 45 degrees, I just know I got to work in the square root of 2 somehow. So when I add those 2 together, I'm pretty sure I'm going to get root of 2 times 5. Is that good? Just want you to follow that so far. Because if I look down the magnetic field, what would I see? Well, if I was traveling down the magnetic field, I would see not a isosceles triangle, because I wouldn't see the bend. If I'm traveling down the magnetic field is going this way through a rectangle that is 10 centimeters on this side and 5 root of 2 on this side. Do you see that? I know this is not the way you probably approach the question, but Flux merely asks how much magnetic field pierces your area. So I took this thing and just laid it on a table and traced whatever the outline is of the rectangle it would make. That's the rectangle it would make. How much magnetic field would fit through it? Now, don't get me wrong. We could do it the long way. There is a long way to do it. And I figure you would probably like to see that way, and I'll show it to you. But right now, this is how I would approach it, because it really states the nature of flux, which is how much of the magnetic field passes through my loop. And right now, I can say that my area is going to be 5 root of 2 times 10. That's the area. In centimeters, mind you. Now, once I have that, I can work the rest of the problem and find the flux. But because I know none of you thought to do it that way, which is why I assigned this problem purposefully, to show you an alternative, a way to consider what flux actually is, I will show you what you did or what you should have done. Let's turn it on its side and look at it. Oh, good. Could you guys just bounce up and down up there? That'd be fantastic. Consider for just a moment this side right here. I just want to consider one side because there's symmetry here. So if I do one side, I can just double it and get the other side. Is that okay with all of you? If I look at this one side, that angle's 45 degrees. And I can just look at this side's area, which would be 5. And then there's the long portion of the side, which is 10. Right? So the area is 5 times 10. The magnetic field is still B. So I would do, for my flux, B dot dA, which would be B times 5 times 10 times the cosine of 45 degrees, which, last time I checked, is 1 over the square root of 2. So this will be B times 5 times 10 all over the square root of 2. And how many sides do I have to do this for? 2. Won't they give me the same answer? Now they tell me what the magnetic field is. They say that it's 5.3 times 10 to the negative 2 Tesla. That's in my problem. I don't know if you guys have the same value for your magnetic field. But whatever your number is, you're just going to plop the number in there. The hard part was this. Now, you can't actually do this and get the answer, by the way. Sorry. Just a few things to clarify. So my magnetic field is 5.3 times 10 to the negative 2. You would have to use yours. That's the B dot A. My area has to be not 5, but 0.05. I have to put it in meters, times the root of 2, times 0.1 to put it in meters. So now I have meters squared there. And that's going to be the flux. Yeah?
Would this work if the angle wasn't 45 degrees? Because I feel like, I don't know. Because I thought
The angle wasn't 45 degrees, then it would affect, let's say the angle was 30 degrees. I don't have to really redraw it for that. And be mindful. What I'm going to show you, yes, it will work. But you have to be considerate of what angle we use. So let's say this is 30 degrees. Okay? So, yeah, this one would change to 30. But then when I look at the other side, is it 30? Now, if it's 30 here, then, this one's 60 degrees. I'd have two different components there because the angle would be different for the two different sides. However, if I was doing this thing right here, I would have to find a whole new angle. But, did I draw it right? No, I drew it wrong. Hold on. Sorry. I still only care about this bottom part. So 30 degrees would apply to all of it. And I would get the same answer, just I'd have to make sure I put cosine 30 degrees after it. So if you want my honest opinion, I'm not sure one or the other of these is better. They're just different. And by the way, that would be 60, right? Yeah. It works out. It's not pleasant, but it works out. For this problem, which is number 20, it's E dot ds is equal to d flux dt minus. I don't have to put an n there because we're just inside the solenoid and there's no loop. I'm looking at the electric field. So I'll do this in terms of R, but this problem actually, I don't think there's a whole lot to it. We're inside the solenoid. So assume that inside the solenoid we have this uniform magnetic field. We are in a solenoid. We're well inside the 5 centimeter radius inside the solenoid. So I don't have to worry about the fact that it's a solenoid at all. All I need to know is that I have this magnetic field that's nice and uniform, but I think decreasing over time or increasing over time. Now, they give us, mine says 5 centimeter diameter solenoid, and it's starting at 2 Tesla, and it's decreasing. So I'm not sure what I'm going to have to do for the answer too much, except for the procedure, which is the R that I'm given is 1.5 centimeters, which means I am interested in something well inside my solenoid. Does that make sense so far? I'm just going to draw a loop. I'm going to draw a loop as if I have a wire inside the solenoid that has a radius of 1.5. That's mine. Your radius is probably some other number. So I'm just going to use R. Is that okay with you guys? But I know that R is less than the solenoid's radius. The solenoid is way out here someplace. I'm just picking something that's concentric with the solenoid because all I need the solenoid for is to provide me my magnetic field. After that, the solenoid's not part of the problem. They're not asking me about the solenoid. They're asking me about an electric field inside the solenoid. So, the right side is still got to be based on finding the flux, which is B dot dA. So the B is some function that depends on time. I'm just going to leave it at that because it doesn't matter for the flux calculation that it's changing with respect to time. The dA is going to be pi r squared, which is the area inside this loop I've drawn. You have numbers to go with that. Great, use them. But I'm just going to leave this as negative d dt of b as a function of t times pi r squared. I'm going to leave out the cosine of 0 for right now because it's in a solenoid. We know that it's a nice collimated magnetic field. I'm drawing my loop so that it's lined up with that direction. Now, this is going to be dB dt. God, that's some messy handwriting, but I know I'm bumping up against the bell here in a minute. dB dt pi r squared with my negative sign here on the right. My left side is, I think we can assume that the electric field stays the same, that our electric field is going to be tangent everywhere on my loop, and all I got to do is add up the length of my loop, which is going to be 2 pi r. Is that okay so far? I don't know direction. That negative sign there is the direction. So I know I'm going to have to deal with that in a minute. But they just want the electric field strength. They didn't ask for the direction. They didn't want the vector direction of it. So I can ignore the negative sign, I'm sure, and write this as E equals the pi's cancel. One of the r's cancel. So r over 2 dB dt. Now I have numbers that go along with this. You know, mine is 1.5 centimeters. So times 10 to the negative 2 to make it meters, divided by 2. And my dB dt is decreasing, 3.7 Tesla per second. So negative 3.7. But again, I don't care about the direction. They just want the size of the magnetic field. I'm sorry, size of the electric field. So the electric field, 1.5 centimeters away from the edge, will be whatever the product of all this is.